Yes. Okay, so thanks everyone for coming. This is into the Alia. So this is a Dalton seminar on manufacturing challenges in fusion. We've got 5 panelists today. So we've got Garreth Aspinall at the far end, who's a program manager of the Fusion Performance Unit at Jacobs. Then Phil Monks, who's a business development manager at the Nuclear AMRC.
Hi.
Then John Francis, who's a professor at the University of Manchester, who holds a chair in Materials Welding and Joining.
Hi, everyone.
And then on Zoom, we've got Will Pearson, who's a director at Hyde Group Nuclear. And then Paul Goodwin, who's the Manufacturing Technology and Equipment Qualification Group Leader at UK AEA.
Hi, everyone.
So I think we've got quite a lot of people to hear from, so we'll get started. And the structure of this seminar is going to be, each panelist is going to give a few minutes on their what they think is the main manufacturing challenge in fusion, or a couple of comments on that. And then we'll hear from every panelist, and then we'll open up to discussion between the panelists and questions from the audience. So we're going to start with Garreth.
Super, thank you. So when I signed up for this, I didn't realise I was going to get asked about the biggest manufacturing challenge for delivering commercial fusion power, which isn't a very easy question to answer, I don't think. It's both broad and kind of challenging. So I stepped back first and I thought I probably can't address the whole of it, but what I can talk about is tokamak style reactors. So I'm avoiding discussion of private fusion and some of their kind of, I don't know, esoteric designs, where they might have liquid lithium flowing down walls and various things like that. So I focus my response mostly around tokamak reactors, which is where I think we're most likely to get commercial fusion power. And I stepped back and thought about some of the 6 challenges that UKAA have set out of fusion. You know, the plasma science and how we confine the plasma exhaust and how we deal with the heat, the materials science and the materials that can actually perform in a fusion environment, the fuel handling, breeding and handling of the tritium in particular, robotic maintenance, innovative engineering. There's quite a lot of challenges there. And fairly recently, Jacobs, along with NAMRC and Vesco, we undertook a review for UKAA of the step manufacturing schedule, focusing on the actual manufacture rather than the upfront design, the kind of testing of bonding and things like that. And the key things we looked at there, we highlighted some areas that we thought were really quite critical. They were the likes of the breeder blanket, the outboard limiters, some areas for supply chain where, although the technology is there, the supply chain isn't. So things like gyrotrons, diamond windows. We also covered things like TF coils and TF conductors, and also the tritium extraction. But if I reflect back on the fusion challenges that UKAA have highlighted, I think probably the most challenging area is the breeder and the breeder blankets, because it sits across many of the challenges. So it confines the plasma, it has to deal with a high heat load, it's in novel materials, it's involved in the breeding and handling of tritium, it's going to need remote maintenance, and it's also going to need quite a lot of engineering. And at the moment, the breeder blanket designs are low technology readiness level, so low TRL. They're early in development. There are quite a few novel designs proposed for demo, and at the moment there isn't yet a test facility for breeder blankets. So I don't know if you're aware, Jacobs are building the Chimera facility for UKAA to test sort of plasma facing components. but we don't actually have something that can properly test a breeder blanket in anger. And then if we look at the ITER program, you might think the ITER program would help you here and help you qualify the test blanket modules. But the test blanket modules, which are essentially several breeder designs that they will put into ITER, the ITER program is going backwards rapidly. So first plasma was, talked about fairly recently as being 2025. I think it's fairly clear that that's gone backwards. The ITER first wall was going to be installed sort of 2030. I think realistically for the test blanket modules coming in, we could be talking about late 2030s, maybe early 2040s. Now that means ITER isn't really going to be able to inform a program like UKAA STEP program, because they're going to be putting their breeder in and testing it in anger, but UKAA will have needed to make their design decisions a long time before that. To give you a brief idea of context on how long these programs take, Jacobs worked on the first wall panel project for ITER. So we designed and manufactured with partners the first wall panels, and we did the first prototype. And that prototype took around 7 years to design and manufacture. And that discounts any time for the actual development of the bonding. So that built probably on a 10-year program of bonding and testing and trialing of the methodology on small prototypes. So in reality, it's quite testing and quite challenging. You might have noticed recently there is some funding, the 650 million alternatives programme announced by the UK government, which will fund things like the fuel cycle testing facility, and that will probably allow testing of the breeder blankets in anger. And STEP's actual aim is to develop the supply chain and show that the systems function together. It's not actually to give you commercial fusion power. So in addition to the breeder blankets, when we're talking about them for commercial use, you probably need to start considering that you'll need development of low activation steels as well to kind of complement that. So ultimately, I think the breeder blanket program is challenging. It's low TRL level, there's long development programs, and the breeder itself performs multiple functions. So it has high heat fluxes, it produces tritium. We're not fully sure how we're going to extract that tritium from the blanket. It probably uses liquid lithium. It will require remote inspection and maintenance, so you need to consider that in the design phase. And from fuel cycle talks that I've been to this year, what's increasingly striking is that relatively small changes in sort of breeder design can give you quite large changes elsewhere in terms of reactor performance. So I think if we are going to meet the challenges of fusion, we really need to work out how we accelerate the breeder blanket development path so that it's ready when we need it.
Thank you very much. So we'll now hear from Will Pearson.
Hi, can you hear me?
Yes, we can.
Yes. So just introduction, Will Pearson, I'm Director of High Group Nuclear. High Group is an organisation of 20 businesses based in East Manchester. Very broad capability, primarily around fabrication, precision machining, assembly of complex equipment. Most of our work is defence, nuclear and aerospace. The focus of the business is around high quality graded, high precision requirements with a significant safety consideration. So most of what we do, I think we term generally conventional, but quite often working at or up to the limits of what's achievable, kind of the edge of the comfort zones. When you get into the edge of the comfort zone, you start to look at some of the stuff Gareth's been describing around ITER, and it's interesting work. It's stuff that we hope someday someone's going to knock on our door and say, we'd like you to make us one of these, possibly a breed blanket. But for us to be able to respond to that as a manufacturer, we have to start now developing capability, which is what we've been trying to do over the last kind of 5 to 8 years, working with, as was AMEC, Jacobs on the neutral beam, but that for ITA, that went backwards. We've tried working with ITA on things for tooling. But you see, in terms of developing that capability so as to be ready for things like STEP, there are some huge barriers around the volume of the work, the language of the work. I don't mean that in terms of coming out in different languages. It's the way the work's presented to the manufacturing supply chain, and just kind of barriers to engagement around ITA, which make ITA not an ideal place to develop that capability to support STEP in the future or fusion programs in the UK. What we've tried to do is look to similar programs. So a lot of the big science programs, ESS, ILL, CERN, have some similar challenges which allow us to build capability and credibility to support fusion in the future. But again, there are obstacles associated with those programs being international projects. Recent work where we've managed to make progress has been on Chimera, again working with Jacobs, looking at commissioning pieces and some of the structures. And what that's shown us is kind of some of the very specific manufacturing problems we face. Now, I think to answer the original questions, what are the challenges? They fall generally into two areas for us. There's all sorts of issues around materials, complex issues, materials, joining technology and things like that, which the manufacturing industry on its own can't solve. Those will be solved in the science. They need to trickle through into development programs, which the manufacturers can then support. But there are still issues, I think, around general geometries, welding access, cleaning processes, size of process equipment like autoclaves for delivering manufacturing process, which can potentially be solved off the back of investment with suitable knowledge around the future demand. So I think what we as a manufacturing industry need to do is work behind the scenes supporting some of the very complex scientific issues and pick off the bits of support we can deliver to solve some of the complex type materials and joining issues, but also engage in a way that helps us to understand the future demand around certain capabilities and physical capabilities around machining, structures, vessels, and manufacturing processes, and start to make the investment cases such that when the knock on the door does come, the infrastructure to deliver programs can be there. The one thing I would say is some of the challenges around manufacturing process we see aren't discrete to fusion. Some of them are conventional, some of them are common to SMR programs, the general nuclear program, as I say, big science. By collecting all those issues together and looking at the commonalities, we can make a much stronger business case for investment in the technologies needed to deliver key elements of a future tokamak or a future fusion reactor in the UK.
Thank you very much. So now we'll move to Phil Monks from Nuclear MRC.
Thank you, Florence. It's rather apt. I'm sat between Gareth and John here. Industry, university, and the Nuclear AMRC actually sits between those two types of organisations in reality. We're there to sort of try and glue the two things together. I'm not going to talk anymore about the Nuclear AMRC. I'm going to talk about what I was asked to do. But if anybody wants to come and talk to me about the research centre afterwards, I'd be happy to have a chat. So, manufacturing challenges, they don't get any bigger than this. Mainly down to the environmental conditions, creating a star on Earth. I've got temperature fluxes between what's laughingly called high temperature superconducting magnets that are operating at a few tens of degrees above absolute zero, a few meters away from plasma at 150 million degrees centigrade. Manufacturing challenge there. Magnetic fluxes, trying to pull everything apart, 280,000 times that of the Earth's magnetic field. Vacuum, 10 to the -8 millibar. That's pretty high vacuum. Neutrons trying to destroy, change the materials that are inside the fusion vessel. And then if you go into other types of fusion technologies such as confinement, where you're trying to spin lithium and compress it all at the same time, the forces that are on those kind of components are absolutely huge. The challenges are massive. Solutions to these, they will evolve, but timing is critical. And I've written something a bit twee here, so forgive me. I put to manufacture or not to manufacture, that's the question. If you go too early, you get failure, materials fail, the plant doesn't meet the potential you designed it for. You miss out on developments and breakthroughs that have taken place whilst you're building the plant. And then it puts into question further investment in the project you're involved with. Too slow, however, you lose momentum. The supply chain lose interest. Personnel move on. Someone else succeeds. Further investment is put under question again. You've got to find that sweet spot between too early and too late. Unsurprisingly, working for the Manufacturing Research Centre, I'm prompting people to go early. It's better to go too fast than too slow, is what I would argue. Doing and failing is learning. Winston Churchill, I've got a couple of quotes now, so forgive me. Success is not final. Failure isn't fatal. It's the courage to continue that counts. And Bill Gates wrote, it's fine to celebrate success, but it's more important to heed the lessons of failure. Oops, sorry. As I said, improvements and developments will continue in physics, in material science, in manufacturing, tools and techniques. But at some point, some brave soul has to stop and build. What you can't do is continue to design whilst you're building. That's a recipe for disaster. And then at the same time, you need to hope that timing is right. So that's the end of that part of my sort of mini presentation. The other thing that I wanted to do today was to appeal. This is a fantastic industry. It's one that needs bright, young things. It needs academics, it needs welders, it needs physicists, engineers. What it basically needs is people like you. And I hope that today's forum gets you enthusiastic about getting more involved in that industry, because it's a great industry that could produce an infinite amount of energy at very low cost, both to the environment and in terms of money. Thank you.
Great, thank you very much. So we'll now move to Paul Goodwin on Zoom.
Yep, hi. So first thing, Paul Goodwin, Manufacturing Technology and Equipment Qualification Group Lead at UKAEA. Listening to the first three presentations, I can understand why I'm so old and grey and tired, because of the challenge. My group has two teams. One team is largely consists of the step manufacturing team, which some of you will have interacted with at times. The other team is the non-STEP funded and looks at some of the lower TRL and more fundamental research issues. So I'm going to first state that I agree with absolutely everything that's already been said by the previous speakers. I've got four main challenges: novel materials, scale up of components, qualification, and supply chain. But you will notice, as everybody else has mentioned so far, supply chain, I will say numerous times, because that's possibly the biggest. So novel materials. Most of you will be familiar with the sort of materials we're looking at. We're using reduced activation ferritic martensitic steels, which are not common materials, copper chrome zirconium, tungsten, possibly vanadium alloys, and we're looking at things like Rebco superconducting magnet materials. They are all relatively novel, relatively exotic, and some of them are still at relatively low TRL levels. We're talking about complex geometries in those materials to make the components that we need. And so we need to accelerate the development of some of those specific materials to get to the scales that we're going to need. Second point, scale up of components. Yeah, most of our work is done on small pieces, lab scale stuff. But when you think of a tokamak, you're thinking meter scale components. You're talking very, very large lumps of metal. And we need both conventional manufacturing. So as was already mentioned, I think by Will, the overlap with SMRs and things like that for large steel components is huge, and we need to sort of work together on those things. We're also looking at near net shape technologies. So that could be net shape casting, it could be hipping, it could be additive manufacture. The advantages of those is we get the complex geometries, and we can eliminate some of the joins that are required. Now, welding and joining is an area which is urgently needs assessment, because we want to eliminate as many joins and welds as possible for reasons that we've already mentioned. That they're often in areas where you can't easily inspect them, or you can't easily make them in the first place. So we want to try and utilize near net shape forming to try and put the welds in a position where they're more accessible, more easy. And most of these technologies, they're around a sort of TRL level 3, and we need them to be up at TRL 6 or 7 as soon as possible, really. And some of the technologies will be rejected for STEP because it's assumed that they're not going to be ready in time for when STEP has to freeze its design. So as Phil was just saying, you need to not carry on redesigning when you start making. You've got to freeze the design at a certain point. That may mean that some of the technologies we want to use won't go into STEP. They'll go into STEP Mark 2, Mark 3 further down the line. Qualification is a huge issue. Obviously, I've got qualification in the title of my group. Yeah, it's a very, very big issue. We're talking about materials qualification. We're talking about manufacturing process qualification. We're talking about inspection technique qualification, facility qualification, and then the qualification of the actual finished components. Huge, huge area. And the problem with a lot of the things that go into a tokamak is we're not necessarily able to do deterministic qualification on all of them. So on a lot of it, there's a lot of probability coming into it. So probabilistic qualification, living with uncertainty. And for us as the manufacturing side, it means we need to tie down the manufacturing process so that it's reproducible, so that you know what you're getting, so that you can then import the data from that into your digital twins, which are going to work out how it's going to perform. So we need, understandable and reproducible defect populations. Ideally, we don't want defects at all, but we need to know what defects are there and that the components are going to be built consistently so that they're understandable, because then we can use the digital twins to predict how they're going to behave. alongside testing like Chimera and other rigs. So living with uncertainty is a big part of the qualification of Tokamak components. So all of this relates to supply chain development, and I think Phil expressed it quite well in saying that it's been stop-start over many years. Fusion has always been seen as maybe 20 years' time, and always will be. And actually, we're now getting to that point where it's actually got to happen. And so, yeah, the time for investment is now, but we have to obviously persuade the supply chain that we need the supply chain to invest in the facilities that are going to be needed. So to give you just a couple of examples, we're talking about things like a large-scale hip, and this overlaps, I think, with SMR. You know, we need a hip of a sort of 4 meters diameter, that sort of size for some of the components that we may need to make in there. We're talking about some higher temperature capability hips. So hips with a temperature capability of sort of 1600, 1800 for some of the tungsten components. The biggest one, I guess, if I had to put my money on the biggest problem, is high volume Rebco superconducting tape manufacture. There is just not enough capability in the world, let alone around the UK, to manufacture the amount of superconducting magnets that are going to be needed. And yeah, that's, if I have to summarize it, is supply chain availability at the right time coming up, and time is getting short, as Phil said. So yeah, there we are. That's my summary.
Great, thank you very much for that. So we'll now hear from John Francis.
Okay, thank you. I'm going to commit the cardinal sin of trying to share a presentation without having tested it beforehand. But let's see how we go. So it's just one slide, actually, and a lot of what I'm going to say, I think, overlaps with what the previous speakers have said, and maybe just saying the same thing in different ways. So for those of you who don't know, my background is in welding, and I've not done a huge amount with fusion. I started out with gas-fired power plants and then came to Manchester and started working on fission about 15 years ago. And the, I guess, inaugural research director at the nuclear AMRC, the late Professor Mike Burke, we were driving over to Rotherham one day, and he said to me, with 30 or 40 years of experience on real plant, you know, John, you're working in a good area, welding, because 2/3 of the problems that happen on fission reactors occur at welds. And I took a note of that. And one of the other things that I've sort of learned over my time working with welding is that it's seen as a downstream process. It's one of the last things that's addressed. Often the materials are developed for specific applications, and you'll do toughness tests, corrosion tests. Yep, this is a viable material. And then all we've got to do is weld it and assemble it into a real structure. So welding, I guess, is one of those things that can cause problems at a late stage. And I'm sort of saying this and gradually sort of come back to what's on the slide. I guess, ultimately, I think the biggest problem, well, there's a few, and this is not an exhaustive list. I imagine that we're ultimately going to need materials performance data. We're going to need to test representative components in environments and under conditions that are as close as we can reasonably achieve to real service conditions. So we're going to need some level of assurance that the components will perform as we hope. And there's a few things that need to feed into that. I think there's the maturity of the design of the reactor. And now, why do I say that? It's not in any way meant to be a slight on colleagues working on fusion technology. That's not, this is a huge problem. But as a welder who's sort of at the end of the line, the first thing I say or ask will be, okay, if you need to design a weld for this, what what temperature are you operating at? What are the irradiation conditions? And you need to be quantitative. In the fossil-fired and other sectors, if you're operating up to about 600 degrees C, you can consider a ferritic steel. But if you push that up to 650, you're straight away, you're out of that arena. You're into austenitic stainless steels. You go up another 50 degrees and you're starting to look at nickel-based alloys, just based on their performance in creep and against other degradation mechanisms. Now, each one of those materials will have a different joining solution, and will have a different range of microstructures that are produced at joints. And what we need to do is, ultimately, I agree that we need to eliminate welds as much as possible, but we won't be able to avoid all of them. And where we can't, we need to be able to test mock-ups as best we can before we consider putting them into service. So even sort of more tightly specifying what we're aiming for in terms of joining is going to be a huge help. Because as I say, a change of 50 degrees means a change of alloy, means a change of joining process, means a change of the range of microstructures that you're going to see. Now, and just by way of example, this is going back to the fossil-fired power sector, who for decades in the 20th century, the maximum steam temperature was 560 degrees C. 2.25 chromium, 1 molybdenum steel was the workhorse steel. And then they thought, okay, if we can increase the steam temperature to 600 or even 650, that's 90 degrees max, we can dramatically reduce carbon emissions and get a greater thermal efficiency out of our plant. That was a 25-year program to increase by 90 degrees, involving creep testing, where you've got components going into service for 25, 30 years. If you don't test for a year in a creep test, industry would often say the tests aren't credible. If you have to accelerate to do a test in 2 months, you're heating the material up, changing the microstructure, changing the deformation mechanism. You're not testing in a regime that is relevant to service. So, and it wasn't until the 9 chromium steels were developed and they started to be tested that it was realized that, oh, actually, there's one particular zone in the world that's prone to premature failure and creep. It's heated to between 900 and 1,000 degrees C. Now, in a weld, you've got all possible permutations. Whatever peak temperature you think about, it exists somewhere in the world, unless you're dealing with a solid state joining process that doesn't heat up. So I think for me, it's we've got these interdependent aspects: maturity of design, availability of materials. If you want to make a weld and test it under realistic conditions, you can't do it on a 100 millimeter long plate. You know, we're talking meter scale. You know, you're probably not even getting up to steady state welding conditions. You're dealing with a transient scenario. Of course, there are things we can do with modeling, but you know, there are limitations. So in order to do that qualification, and so I'll rephrase the top box there, materials performance data, that's really a step towards qualification. We're going to need maturity of design, availability of materials in quantities of engineering significance, something you can make a representative mock-up out of. And then we're going to need to tailor the welding processes to those alloys. And these are all interchangeable. Yeah, so that process over 25 years for the fossil-fired sector involved tweaks to the alloy composition to make it more weldable, to improve the creep performance. You know, but so I guess it's a multifaceted problem, and each one of the I guess knowledge streams that feeds into this process is interdependent, and that makes it incredibly complex. So I've raised, I guess, a range of problems. I didn't mean to do that, but I wanted to just give you a flavor from the working at the downstream end on larger components, even albeit from academia. Okay, yeah, thanks.
Great. Thank you very much. So that's been really interesting. There's a whole massive range of different challenges with manufacturing for fusion. So interesting to hear from everyone. Does anyone have any questions for the panel, or questions between anyone on the panel? Have questions for each other? You.
Yeah, not a specific one, but since you raised loads of questions, there seems, I mean, like challenges and obstacles apparently, and one of you also stated that fusion is always 20 years ahead. And do you ever feel like disappointed, down, in your work? Do you ever feel that it's not going somewhere? Or I don't know if I'm picturing a bad picture or just want to think.
It's a bit of an up and down thing. I mean, 12 months ago, General Fusion were going to build their first demonstrator here in the UK. They made the decision that their design wasn't mature enough to invest that amount of money, and they withdrew to Canada to do an interim. They say they're going to be back, and when I look deep in their eyes, I believe them, because the thing with the UK is the environment that we've got for fusion is probably as attractive as anywhere. And we've built over a period of time a cluster. We've got a government supported fusion reactor being built. It's got a site. We've had inward investment by to varying degrees by a number of different fusion companies, and they're all interested in what's going on in the UK. So on balance, compared to where we were 5 years ago, I think it's really positive, but you still get the bumps in the road like General Fusion.
I think I would add the biggest frustration is what Phil's describing, but the bumps in the funding. So you get the message out to industry that, you know, steps happening, the funding is coming, and that works for about a year, and then the next year there's rolling back on the funding, and then you get for the following year a government announcement of 650 million. You're never quite sure what's going to happen the following year in terms of the funding scenario, and that makes continuity of development quite difficult, I think, and upsets. When I'm saying the supply chain is really important, it upsets the supply chain, because we appear at UKAEA as if we're turning the tap on and off all the time, and actually it's not us, it's it's the government and what they give us. That's the biggest frustration, that we can't get a consistent long-term message out there because the funding goes up and down.
And I think to echo what Paul said, you know, as the supply chain, as the manufacturing business here, it is so hard, therefore, to put a business case together, whether that is investment in equipment or whether it's investment in people. And don't worry, Paul, we don't blame you personally, but that is why that's why the dialogue piece around where we're going to be in 5 years' time, 10 years' time is so important. Because what I do fear is at some point all these breakthroughs will happen. There will be the knock on the door, and UK manufacturing supply chain, as it did with Hinkley C, will turn around and say, "Well, no, we can't make that. We've not prepared for that. We don't know what that is." So that projection is really important, and then the bits that fill in the gaps from other projects will help to build the capability we need.
Following on from that, really, so the supply chain is really important, but I think one thing that fusion struggles with is it's still a very small industry compared to oil and gas or some of these other industries. And when you're talking to companies in the supply chain, a lot of them just don't want to make anything because it's not worth their while to put all this money for a very small contract. Is there a way where we can work with other industries? Because I think a lot of the technology is very transferable, whether we're talking about joins, high heat flux components, some of the superconducting materials that we've discussed. Is there a way that we can be more joined up with other industries so that we can develop the supply chain more?
Can I just check you heard that on Zoom, the question?
Yeah, I did. And I think it depends on the material. So some of the challenges are materials based. So for instance, we need a lot of tungsten, but very often you look around and say, well, actually, you know, who in the UK can machine tungsten? Because most things are bought from China and they're bought ready machined. And if you try and talk to the supply chain saying we need to be able to machine tungsten better, they'll say, but where's the throughput that's going to justify any investment in that? Similarly, we've talked about vanadium as a possible material. There is no supply chain for vanadium. Certainly in the UK, there is zero supply chain, I would say. And you look around at other industries and nobody else wants it. So, yeah, when you're trying to get funding, if you're trying to get public funding through Innovate UK or something like that, what they want to see is how the technology is going to spin out into other sectors. And with the best will in the world, vanadium isn't going to spin out into other sectors. It's very, very fusion specific. So yeah, it depends on the material, I think. Sometimes there is a good alignment with other industries. Sometimes we're on our own and having to sort of try and fund it from its fusion specific, and we're the only ones who really want it.
I'd say, well, firstly, the investment in fusion over the last, now I might have these numbers wrong, but they're more or less right. In the last 2-3 years, the amount of funding that's gone in is greater than the fusion that has been in, the money that's been invested in fusion for the previous 10 years or 20 years. So I don't necessarily think it is the money. I think it's where we're at. And if you're a physicist, a fusion physicist, you're in high demand. But as I was trying to allude to before, at some point, you've got to put a stake in the ground like ITER did, perhaps too early in their case, and start building something. And at that point, you will engage with the supply chain. But at the moment, it's not so much supply chain work, it's more design, it's more physics. I want to get them, because I work for the Research Centre for Manufacturing, I want to get them away from that towards making mistakes and learning.
I think on that point, it's I would look back and think about what we did on the hip bonding. And Paul mentioned there in his talk about the need for a very large hip facility. So we explored this about 4 years ago with Fusion for Energy. So they felt they needed a very large hip facility. We had some conversations, predominantly in the UK. Bodyco are the main provider of hip. They provide it across Europe as well. And the panel we made was a prototype which just fit in an existing facility in Hereford. And Fusion for Energy wanted to build a bigger hip vessel. There's one in Japan that would just about fit all the panels, but it couldn't go up to high enough pressure. And so there's no interest from Bodyco in building a big facility. You'd have to give them the money. And in the ITER situation, they were like, well, you've only got 400 panels, and some of those can fit in existing facilities. So in reality, you're down maybe 200 panels that you need a bigger hip vessel. And you're only doing sort of 2 hip processors per panel. So it's just not actually worth their money. So a big hip facility, a standard big hip facility, is about £30 million if you've got the infrastructure there. And they would need to make that money back. So rather than going down that route, what we did at Jacobs was we looked about how we could modify our processing to get the panel into existing facilities. So we did a whole series of work around testing and mock-ups to close the gap at a lower pressure. So we managed to reduce the pressure from about 140 megapascals to about 100 megapascals. And that meant that all of the panels that are going to be made for ITER can fit in existing facilities. And it's that kind of innovative approach that I think we need to take to manufacture, rather than immediately jumping up and saying, we need a bigger HIP facility. Well, maybe we don't need a bigger HIP facility. Maybe we need to make panels that fit in existing HIP facilities, and we need to modify our process. And that's how you will accelerate the manufacture, I think, and get yourself in a position that you can make some of these components.
I wouldn't disagree with that. I mean, I think the truth is we need a bigger hip, but we're probably not going to get a bigger hip for the very reason you've outlined. And it's then, okay, if you're joining together smaller bits, where do you put the joint? How do you design it for manufacture? Yeah, given the constraints that you've got. So yeah, I don't disagree.
Likewise, I think you're spot on there. I think it's an issue we've seen on Chimera. Just take it away from HIP, other processes like cleaning processes, you need large cleaning baths. Okay, well, an investment case can be made around that. The volume of parts might be there, but it's not available overnight. We need to understand that flow of stuff. And that's where, going back to the question, the link with other industries are there. If you can make a business case that says we need a big bath for cleaning things, it can be used across industry, not just fusion.
Yeah.
Great. So, other questions? Should I go?
Okay, so thank you for your presentations. So my main question is that we've heard like different checkups, UKA, all this stuff. So as far as I can see now, it's like divide and conquer. What about what's the main route to actually tackle those things? Because we only said the challenges so far, and then we have a problem, we need a heap, we need that. But what are we actually doing to tackle these problems? Is there a main line, or is everyone separately trying to join things together?
Well, I'll start. We work for both the UK Fusion project, STEP. We also work for private companies. Those private companies, at the end of the day, they're very protective of their IP for obvious reasons. However, they do come together. They have typical problems. We run things called joint industry projects, where organizations with similar problems come together because they realize that by pooling resource, they'll get more bang for their buck. So it's a weird environment where, and not dissimilar to fishing, where you've got frenemies. So one minute you are friends and working together, and the next minute you're fighting like cats in a bag. So I don't know if it probably doesn't answer your question, but it's very similar to most industries in a commercial world.
I think I'd add from the UKA side, our job is to deliver fusion. Now, I could be very altruistic and say ultimately that doesn't matter whether we deliver fusion or a private company delivers it, as long as it's delivered. And there is a huge degree of truth there. As Phil's mentioned, there's also IP issues. And as STEP becomes a more commercialized organization through UK IFS that's being set up, that may well become slightly more of an issue. At the moment, on sort of fundamental research, if it's not STEP funded, the first thing I do when we have an idea is to contact Tokamak Energy and see if they're on board as well, because I know their challenges are just the same as us. So we do work together to that degree. I think what the questioner is asking about is further down the line in terms of supply chain collaboration. And that's, yes, that's above my pay grade, really. That's consortia and decisions that will be made higher up to try and bring everybody together to deliver, rather than working in a sort of siloed way.
Thank you. Should we move on to Josh's question?
Yeah, thanks. I'll preface this by saying that I've got skin in the game in my PhD project. But given all the challenges that you've outlined so far, is it wise or pragmatic for us to be self-imposing problems or challenges like reduced activation on ourselves in our material selection, in the way that we conduct ourselves? Why are we kind of making things more difficult than they need to be?
I was gonna, that sounds like one for John or Paul. I'm gonna do the old slopey shoulders on that one.
I don't mind. I can, perhaps Paul can follow on with a more detailed answer, but obviously, if we are creating materials that are active, there are health hazards, environmental hazards. To put it mildly, the problems from fission reactors have not been solved. Yeah. And we are creating this legacy in which we've got a lot of hazardous material that we don't know what to do with. It would be a real pity if we, didn't learn from that in some way. It does make things much more difficult because you're trying to achieve. It's a more tightly constrained problem. But I think Paul's probably much better placed to say, speak in more detail.
Yeah, I mean, you can argue it's a self-imposed limit. So we have a limit that we don't produce anything that has a half-life of greater than 100 years, basically. And that's one of the. I'm really simplifying here, so I've got colleagues who can give you more expert opinion, but. It's not only that obviously the material you start with, but what happens in the transmutation during irradiation. So tungsten some of it will turn to osmium and other isotopes. And similarly for the steels, each of the elements in there can transmute. There's a lot of studies gone into it, and we do have a very limited palette of acceptable elements in different parts of the tokamak. And that's what's led to the development of the Rapham steels. The only other alternative is to go down the route that we're going to produce lots of radioactive stuff, which we have to handle separately, and the danger of something being radioactive for thousands of years. Which the whole selling point of fusion is that it's clean energy, and it's a big step to say, yeah, we're going to produce clean energy, but actually you're going to have to deal with stuff for thousands of years afterwards. That's a simplistic level. It's much more detailed and complicated than that, but it is a limit that's been decided.
I'm sympathetic to that idea, and I think it's important that we acknowledge kind of intergenerational parity and that kind of thing. But I also can't help thinking that we're letting better be the enemy of good enough, as it were. But if we loosened the restrictions on ourselves a little bit in the interim period, we could improve on the design later on.
I think there might be a halfway house. So I think rather than it being clean energy, we might have a halfway house which is cleaner energy, and you could see that as kind of being fast to market, really. And I think the real challenge comes with whoever can first demonstrate proper fusion, sustained energy producing fusion, regardless of whether that plant is active or not. I think they will be the ones that get the most funding. And as soon as you demonstrate that, a huge amount of funding will come your way from private investors.
I think what I'd say is you need to be careful, because whilst you might speed up the process in one area, you're then going to move away from the health and safety executive and the environment agency to the NDA, and that ain't going to be a quick move once you get the nuclear guys involved. And by that I mean the regulators. It's going to slow things down.
However,
Yeah.
isn't that faster? Are we not gonna acquire more data by trial and error rather than assuming and waiting? Because this way, if we were like actually give like ourselves a little bit of more room, we would have more data, so we could assess the situation better.
Yeah, and you can do that and go around that loop ad infinitum, but at some point, all of the modeling, all of the design, all of the physics can only take you so far until you actually, press the green button, it switches on, and Q is greater than 1, and Q is greater than 1 in a realistic way, not the sort of half falsified way that they did it in the States not too long ago. And I don't mean that to sound derogatory, because it isn't. They did get more out than in, but it was a bit of a dance to get there.
A thing I'd add, I think Gareth identified it in his talk at the start, that one of the key area is the breeder blanket. And the breeder blanket needs to operate in the region of sort of between 600 and 700 in order to get the tritium breeding ratio sufficient for feeding tritium back into the start of the process of the fuel cycle. And it's the materials challenges around what do you make the breeder blanket of, and what is the breeder material that it contains. And there's where we're really struggling, I think, to have a material that meets the requirements. And I think if there comes any point of relaxing on the materials palette, it might have to be there. But for the reasons that Phil just outlined, the fact that you open yourself up to regulation by nuclear industry would be a very serious consequence of that.
Great, thank you. I think we've probably run out of time now, so thank you everyone for your thoughts and your contributions and for the questions. Do you want to give everyone a round of
I just I will hang around for a few minutes if anyone has any additional questions that you want to ask. I was, I think, saying that I needed to get away, but that meeting actually now has been postponed, so I'm happy to hang around for a few minutes afterwards.
Okay.
Thank you.
Yeah.
Thank you.
Similarly, if people want to contact me offline, by email or whatever, please feel free.
Thank you. Thank you.
Everyone.
Willing to call.
People for taking this up.